So my name is Adela, and I will present you today our difNLR package, which is joint work with Patricia Martinkova. So what can you expect from this talk? First, I give you a very brief introduction, and I will list some methods that are already implemented in R. And I will use our solution in difNLR package in two functions, first called difNLR, and second is dfNLR. And I will also present one Shiny application called Shiny Item Analysis. And I will end with some future steps. So let's start with introduction. So where can you use our... Yeah. Okay. Where can you use our package? Our research is interested in multiple item measurements such as educational tests, assessments, questionnaires for psychological diagnostics, etc. Why would you use that? You want to check item fairness. You want to be sure that your tests and items are fair. And you want to check there in some social groups, which can be, for example, gender or language level. You want to compare language learners and native speakers, for example. If you want to know more about this concept, you can read our new article, which is available online. Technically speaking, this concept is called differential item functioning. Is the situation when two subjects with the same underlying ability but from different social group have different probability to answer a question correctly. So let me show you this on figure. As you can see, there are two groups, one reference and the second is focal. Reference is usually a majority and the focal is minority. In the first figure, you can see that the curves of probability are the same for all levels of ability. There is no diff. The conclusion is there is no diff. In the second figure, you can see that one line is above the second one, and this is called a uniform diff. The one group is advantage over other. And in the last figure, you can see that this change with ability level. With small levels, one reference group is advantage, and then the focal group is advantage. So this is called non-uniform diff. And I will show you an example of such a diff item. It's a real example from assessments in Czech Republic, and the question was, deficit of vitamin D in childhood could cause, and options were rickets, scurvy, wolfism, and mental retardation. And the correct answer was rickets. In this item, women have a higher probability to answer it correctly when comparing with the same ability. And it is that it's up to a content expert to judge whether this item is fair or not. We can say only if it's diff or not, but we can judge about the fairness. So, yeah. Now I will list some examples or methods that can be used to detect such potentially unfair items. You can divide them in general two groups. First is based on total score, and the second is based on latent ability. In the first group, the example can be Mantel-Hansel test. It's very simple and easily implemented method, but unfortunately, it doesn't account for possibility of guessing or inattention, and moreover, it cannot detect non-uniform diff. The second example can be logistic regression. Again, it's simple. It can detect both forms of diff, but again, it doesn't account for possibility of guessing or inattention. There's a second group. The representative of this group is item response theory models and tests based on them. Technically speaking, there are nonlinear mixed effect models. They can detect both forms of diff, account for guessing or inattention, but unfortunately, they are more complex and very computational demanding, meaning that you need, for example, 500 people in one group to be able to fit the model. So we were thinking, is there any method that can handle these things, both type of diff and also guessing or inattention, and you don't need such a large sample size? And we got one idea, and it's now implemented in difNLR function. I will explain it very simply. This is only the logistic regression with one covariate, which is the total score. And what we did was then we add asymptotes. Now the parameter C can be explained as probability of guessing, and D can be seen as probability of inattention. And of course, in this model, you can introduce group membership and be able to test for diff, such like that. You see there are two curves, and this is actually a non-uniform diff. Okay, so some technical details about our package. We used z-scores instead of total score and IRT parameterization because we want to compare our estimates to IRT models. So the main difference between our model and IRT model is that instead of z-scores, IRT models used latent ability, which is a random effect of the student. We do the estimation by nonlinear least squares, and what we offer 6 models with several constraints on the parameters C, D, or A. We offer also the detection procedure based on F or likelihood ratio test, and we also offer multiple comparison corrections. There's article in review process, unfortunately, about our models, and there is a simulation study which shows that our models are satisfying in diff detection and need a smaller sample size than IRT models. Well, there's an implementation in difNLR package. I use for it dataset GMAT2. It's scored test with 20 items and one group vector. Correct answers are marked as 1s and incorrect with 0s. And the group membership vector means that one is the focal group and 0 is a reference group. If you know difR package, the syntax is very similar, so it's very easy to fit the model, and the output is just like that. And we can see that 2 items were detected as diff, and it was the first and the second. What we offer is also some graphical presentation of the results. They are plotted not only the probability curves, but also empirical values of probability. So, thinking deeper, what about when we have unscored data? The situation in diff, we only model this line, the correct one, but we don't know anything about incorrect answers. This situation may be as in figure 2, but there can be differences between a reference and focal group, similar as diff. This concept is called differential destructor functioning. So, technically speaking, subjects with the same underlying ability, but from different groups, have different probability of option selection. We came with solution for this thing. Very naturally, it's multinomial regression, and it's implemented in difNLR package with dfNLR function. So when we take unscored version of our previous dataset, now call it GMAT2 test, you can see the group membership as well, and we need key of correct answer to be able to fit the model as well. So the syntax is very similar, and now you can see the output, and we can see that item 1 and 2 are again DDF, and moreover there is a item 20 which is now DDF and previously not was diff. And there is also a graphical representation of the results. I know that psychometricians not always like R, so our package is now exploited by a Shiny application called Shiny Item Analysis, and it's available on CRAN and also online. It looks like this. You see there is our difNLR function, and there is ddfNLR. And if you want to know more, just visit a Friday talk on Shiny section called Teaching Psychometrics and Analyzing Educational Tests with Shiny Item Analysis by Patricia Marcinkova. And I will end with future steps, or what can you look forward to. In difNLR function, as I said, we are using nonlinear least squares, and we are planning or working at weighting nonlinear least squares, algorithms, and other methods. Next step would be also implementation of models which allows different asymptotes for different groups to be able to handle a situation just like this on figure. And in dfNLR function, we would like to apply a similar approach as in diff to be able to model something like attractiveness of distractors, because when you use multinomial regression, the situation is that one distractor goes to the probability of 1, and other distractors go to probability of 0, what is not really natural, but this is not what you expect of that, and you want to show some attractiveness of it. So we are desiring this kind of model, and moreover by introducing group membership to be able to test also DDF. Unfortunately, the situation in this model is something like that, so if you have any ideas how to handle these models, any ideas are very welcome. And I will end with this. Thank you very much for your attention.
Thank you very much, Adela. So we have plenty of time for questions if people have some questions or perhaps some ideas for Adela and her future work. Mm-hmm.
An interesting extension could be to look at the asymptotes and how they might change, for example, for the first third versus the last third. For example, inattention may increase as you work on a set of items, and you may lose some of your attention, and that therefore the asymptotes may be different for the first n items, and then they may actually go down or up. I
actually know this approach, but the interpretation was very not desirable, but I know what are you talking about. Thank you.
Anybody else? No? Okay, well let's thank Adela once again, and we can get set up for the next talk now.